So thank you for inviting me to give this talk. I'll be speaking about higher topological complexity of Seifert. Maybe I pronounced this wrong. Is Seifert the correct way to pronounce, or Seifert? Okay, manifolds.
Yes,
fibered
Seifert.
manifolds.
He was German. So.
Okay, Seifert fibered manifolds. This is joint work with Navnath Dankar, who's a postdoc here at IIT Bombay, and Soumyadeep Pandar, who's just finishing up his PhD. I should do a quick disclaimer that I'm not a low-dimensional topologist. I'm actually a stable homotopy theorist by training. So the manifold part is new for me. All right. Okay, so topological complexity of a space was introduced by Farber in the context of coming up with motion planners for robotic movements. And the idea was to understand if one can continuously create paths between a pair of points, A to B, as A, B keep varying. Okay, so more formally, this could be thought of as whether we can have a continuous section of this fibration, which goes from the space of paths to X cross X, and basically takes a path to its big starting and end point. If this map had a continuous section S, then you would have a motion planner. Except it turns out that such a thing will only happen when X is contractible. So obviously you want to be able to do this for more spaces. So the topological complexity of X is therefore defined to be the smallest K that one can find, such that you can find an open cover U1, U2 up to UK of X cross X, such that on each of these open covers, there is a continuous section to this map pi. Okay. Now, there are some immediate facts that was also all proved by Farber, that this is what I just said already, that topological complexity of a space is 1 if and only if X is contractible. TC is homotopy invariant. It's always bounded by 2 times dimension of X plus 1. The part that we are interested in this talk is the fact that TC of a space can be bounded by cat of X minus 1 on top and cat of X on the bottom. So what is cat of X? This is the loose, so I'll say LS category so that I don't get the pronunciations wrong. So LS category was defined as the smallest integer R, such that X is covered by R open subsets, U1, U2, UR. These U1, U2, UR are such that they will be contractible inside of X. Okay, or another way to say the same thing is that the inclusion map from UI to X is null homotopic. Okay. Now, so there are a few nice facts about LS-cat, which we'll be using in this talk. So it was proved by James that cat of X cross Y is bounded by cat X plus cat Y minus 1. And if you have cohomology classes U1, U2, UN, which are non-zero, with the property that when you take their cup product, that also turns out to be non-zero, then cat of X will be greater than or equal to n plus 1. So finding the largest such n is called the cup length for X in this case. And so another way to see this would be that cat of X is bigger than or equal to cup length plus 1. Yeah. All right. So what we want to talk about then is, so we already said that LS-cat will bound TC below, it will give a lower bound, but one wants to do better, for instance, like to compute LS-cat, we have a cohomological lower bound. So there is a similar lower bound that one can describe for TC as well. Okay. In order to do this, let's first define a slightly general notion, something called the Schwarz genus of a fibration. In particular, topological complexity will be the Schwarz genus of the fibration pi from X, which takes path space to X cross X. So given a fibration P from E to B, Schwartz genus of B with respect to P is the smallest number of open sets covering B, such that on each of these open sets, we have a continuous section for the fibration. Okay. So then for any fibration of this form, Schwartz showed that given non-zero cohomological classes, which under P star go to 0, such that their cup product is non-zero. So any k length of such things which give you a non-zero product in cohomology of B, but when I look at their image in the induced map, the images of these elements is 0, then genus of P will be given by, will be bigger than or equal to k plus 1. Okay. So let's look at the case that we are looking at. So we are looking at Schwartz genus of this particular fibration. And x to the I is always going to be homotopic to x by taking a point to the constant path at x. And then there is a diagonal map which takes x to x comma x, and this whole thing is a commutative picture. Now this in homology induces a picture of this form where the homotopy equivalence then induces an isomorphism on the homology. And when we wanted to compute the, give a lower bound for the Schwartz genus, we wanted these classes which under P star go to 0 and their cup product is non-zero. So we are basically looking for classes in here which go to 0 under pi star, and looking at this commuting picture, and this was all proved by Farber, it is clear that something will go to 0 under pi star if it will go to 0 under this diagonal map. So one can talk about the ideal which consists of, which is the kernel of this map delta star. We will, these are called zero divisors of H star X. Okay. So these are all classes in H star of X cross X. And the zero divisor cup length of H star X will be the length of the longest non-trivial product that one can construct using these zero divisors. And then from what was proved, what was mentioned earlier, this will tell us that PC is going to be bounded below by this zero coupling. Okay. So in the case of Sn, one can look at the cohomology of Sn. It as a graded algebra, it's just generated by one element, and we get a non-zero element in H star. So using the fact that H star of Sn cross Sn over a field with field coefficients is just isomorphic to H star Sn, tensor H star Sn, we get an element of the following form, which can, where A is the generator of the graded algebra of a graded ring of Sn. Okay. So then one can check, this is a zero divisor, and the product of A bar with itself is 0 when n is odd, and it is non-zero when n is even. Okay. So this gives a different lower bound when n is odd and a different lower bound when n is even. One then computes the upper bound for this, and using this gives actually a sharp lower bound. So one is able to show that in the case of the odd Sns, TC is actually given by 2, and when n is even, TC of Sn is actually 3. All right. So this was a nice example in which this lower bound and cat as an upper bound will be helpful to actually compute TC. But more generally, this does not always give a sharp lower bound. And there is the idea is to come up with a slightly better bound for this. And there was a notion of weight associated to any cohomology class, which was introduced by Fadel and Hosseini. They showed that, the LS cat of X is always going to be bigger than or equal to the category of the weight, category weight associated to a product of cohomology classes, whose product is non-zero, and this will always be bigger than or equal to the sum of their category weights. So, so I have here defined this, but I want to actually go into a more general case. But more importantly, if each of the elements that are chosen are such that the category weight is greater than or equal to 1, then this sort of gives a similar bound to what is happening using cup length. So if you can actually find elements whose category weight is bigger than 1, then it gets interesting and one is able to say something, get a better bound on cat X. So this was generalized by Farber and Grant for any fibration in the following manner. So let U be a cohomology class on the base space and P from E to be a fibration. And then the weight of U with respect to P is defined as the maximum K, which can be found such that whenever you take any set of maps from Y to B, F star, the induced map on homology will take U to 0. And this is for all choices of F such that the genus of the pullback fibration F star P is less than or equal to K. Okay. So here F star P is the pullback fibration. So this is E to B, and you can pull it back along here and you get a fibration of this form. So for this definition, they were then able to show that if you take cohomology classes whose cup product is non-zero, then genus of P is strictly bigger than the weight of their product, which is always will be greater than or equal to sum of their weights. Right? So in particular, whenever so a class will have weight greater than or equal to 1 if its value on the when you push it along the induced map P star, it goes to 0. So in particular, in the case of the fibration that we care about for TC, all 0 devices will have weight greater than or equal to 1. So this means that what we were already getting was this, because we know that when this is the sum that I get when I look at the 0 cup length for the 0 devices. But basically what we are looking for is cohomology classes whose weight is strictly bigger than 1. So, so Farber and Grant use the idea of stable cohomology operations to then construct elements of weight which will have strictly greater than 1. Okay, so which now we describe. Yeah. So the reason that so maybe the lemma immediately is not so the main. So this is the result that we generalize for TC and case later on, which is why I've explicitly stated this. So in the case of the fibration for TC, what they proved is that if you take any map from Y to X cross X, so it always looks like a map from Y to X, phi, and another map psi from Y to X, then genus of F star pi will be less than or equal to K if and only if you can cover Y by K open sets on which these two maps are homotopic to each other. Right? So just to recall, a stable cohomology operation of degree I is a family of group homomorphisms, H star, going from H star to H star plus I. The coefficients can be different, if you like, which exists for each star. And these maps will commute with all, with the suspension isomorphism and any connecting homomorphisms that we have in long exact sequences. And then excess of a stable cohomology operation is defined to be the maximum K, so maximum value that K takes, where K is, where U is of degree K and mu of U is equal to 0 for all such U of degree K. Okay, so the excess is defined to be this plus 1. So in particular, the Bockstein mod P operation has excess 1 greater than or equal to 1, and SQI has a excess greater than or equal to I. So what they showed is that if you start with a stable cohomology operation of degree I with excess bigger than or equal to n, and you pick any cohomology class in Hn of xr, then the TC weight, I mean like weight with respect to the fibration that we care about for TC, the weight of this particular element is greater than or equal to 2. So what is this element? Basically, we are taking, so whenever we write the bar, the notation is basically we are taking the primitive sort of element. So it's 1 tensor mu u minus mu u tensor 1. This is an element of h star of x cross x. And this always is same as if we took 1 tensor u minus u tensor 1 and applied mu to it. So we use these ideas now to give a fairly sharp bound for Seifert fibered manifolds. Okay. So the cohomology of these manifolds were in ZP coefficients were calculated by Bryden and Zwengrowski. They actually have another paper with 2 more collaborators, but the particular, like the second paper is more general, and that's the idea which we use. Okay, just for completeness sake, I'm just quickly going over what a Seifert fibered manifold is. So we are only looking at the oriented case, and an oriented Seifert fibered manifold is a oriented 3 manifold with a compact genus G surface F. So it's the information that comes along with our manifold, and I forgot to write N here. So comes along with it is a manifold N, a compact surface. So we only consider a compact surface F of genus G, and a map, which is almost always going to be, it's just almost everywhere, a locally trivial S1 bundle. So, but what does this almost mean? So when we, around every point, there is a Euclidean neighborhood like a disk, like around every point in F, there is a disk, such that when I look at the pre-image of the disk, it looks like a trivial S1 bundle, but quite not exactly, in the sense that this is not a projection. This map P is given by taking any pair of points here. So we are denoting it by RT1, T2, where T1, T2 are in S1. So we're thinking of this as R as varying between 0 and 1. And this gets mapped to RT1 to the A times, there's no comma here, sorry. So this should be a product. RT1A, T2B, right? So this gives me an element of D2. So since we, this pair AB is considered, should be, these A and B are co-prime, and A is assumed to be non-zero. And since we assume F is compact, there'll be finite such cover for F. So any such manifold is uniquely determined by the following data. That is, we need to know whether the surface is oriented or not. What is the genus of the surface? And these finitely many finitely many fibers, they are determined by this pair AI-BI. Okay, so maybe there are M of them. So we basically considered these 2 cases where F is non-oriented with genus G and F is oriented with genus G. Okay. So Bryden and Zwengrowski gave ZP cohomology of both these cases. Just because this becomes elaborate, I'm mostly only going to talk about MO, but we are able to do the same sort of thing for the case when the base space is non-orientable, the idea sort of thing. So the cohomology looks fairly complicated. There are all these generators, some of them in degree 1, some in degree 2, and one in degree 3. And then depending on how AIs and BIs behave, there are a bunch of relations on them. So in the case that prime P is equal to 2, this is the relation they have. I think I've also written down. For more generally, if I assume, sorry, I think it's here. So we choose NP to be such that if we use the fact that this is co-prime and choose some DI and BI such that this is equal to 1, then these CIs and DIs are not 2 mod P. So these are all the I's for which this is the case. Okay. Then if we assume that NP is bigger than or equal to 2, then there are further relations between these alpha I beta J's, and also one can talk about the mod P Boxstein, how it behaves on these elements. Okay. In particular, in the case n equals for NP, I mean, when P is equal to 2, they also show that the Boxstein on alpha 1 is going to be alpha 1. I mean, I think alpha I is alpha I squared. I forgot to put that. Okay. So this is, I mean, P is 2, so I should say B2. Okay. So we basically want to use this information then and be able to construct elements of weight 2 and give a sharp lower bound on PC of the Seifert fiber manifolds. Okay. So in these lines, the theorem that we prove is that, so we have to assume a few conditions so that certain things, certain products turn out to be non-zero. And we are able to show that cat is equal to 4. This was also, for some of the cases, was already observed by Bryden and his co-authors in the first paper, where they were working with genus 0, G equals 0 case when genus is 0. But the same sort of logic generalizes. But more importantly, we need to compute this to give a upper bound on PC of M. Okay. So it's just based on how the cohomology works. Under the assumptions that we made, it's not very difficult to show that in one case, either alpha I, alpha j, alpha k, their cup product is non-zero, or alpha I cubed is non-zero. Okay. Which will tell us that cat is bounded below by 4, and the upper bound is just given by dimension of the manifold. Okay. But more importantly, since cat is 4, this bounds the TC by 7 on. And if we want a lower bound, we note that in the P equals 2 case, the Boxstein of alpha I is alpha I squared. And we construct, since Boxstein is known to have an excess of greater than or equal to 1, we construct the primitive for B2 alpha I. Okay. And we basically show that this particular element is non-zero. Okay, so from the earlier mentioned theorems, these two elements will have weight 2. This is a weight 1 element because these are alphas are all degree 1. Sorry, nothing to do with degree, but these are weight 1. So in general, this when I add up the weights of all of these, we get a lower bound of 5 plus 1. Right. Ideally, we'd like to do better, and we did think some about in the cases where we can say M actually has some nice free action on it, then we can probably save the exact value of TC for them. So what we want to do then is use all these ideas and compute TCN of a space. Okay, so let me just quickly go over definitions of TCN. Are there any questions before I move on? Okay.
Rekha, could I ask one question to clarify? So is M always a closed 3 manifold? So the base space, does it have boundary components, or I missed
yeah,
that?
so I'm assuming it's closed for now.
Okay, okay, thank you.
Perhaps, could I ask a quick question?
Mm-hmm.
It's just about the capital O in the notation for the data that goes into the Seifert manifold. So ONG E.
Mm-hmm.
What's
so
the data?
I think it comes from the fact that we are working with orientable Seifert manifolds.
The total space is orientable. I see.
Yeah.
Okay. Yeah. Thanks.
But very honestly, I've not looked up what the non-oriented version would look like. So, but. So in this, we are not assuming anything about the boundary, but I don't know if, like, for instance, Bryden and Zverensky do cohomology in more generality or not. So that's also something to look up. Okay. So Rudiak defined the higher topological complexity as the Schwarz genus of the fibration phi from X to so let me, Jn is basically a wedge of n copies of I, the interval 0 to 1. And then we're basically looking at the map from X to the J, like all maps, paths from, so these are like n paths in X going into X to the n, where since all of these paths have the same starting point, we're looking at where all these paths end up at, right? It turns out that this is nothing but the same as, or this is fiber equivalent, instead to look at the fibration where we're really taking an interval. So we're taking an interval 0 to 1 and splitting it into n smaller intervals. And then we are just saying, we are taking the projection down to each of these points. Okay, so this also makes sense in the motion planning questions where you may have fixed, instead of fixing 2 points A and B, you may be looking at paths between n fixed points and how that changes as you move the points around. So for the purposes of this talk, we are going to think of higher topological complexity as genus of this phi prime, which is taking the path space to end projection onto n different points. So Rudiak showed that this is again going to be a homotopy invariant object. And in this second sort of notion, it's clear that TC2 is just same as TC, which we defined earlier. They have like this, I guess TCN as it goes large, as n goes larger, becomes, I mean, could technically become much larger because obviously we're asking for more constraints here. And the interesting part is that one can show that TCN of X, this is of course less than or equal to cat of it is bounded by, I guess, sorry. Did I miss an n here? Like I think this is bounded by 2 cat of X minus 1. And I think I want maybe here there's probably a 2 here, all right? Then you use the, 2 cat of x to the n minus 1, and then one uses the fact that one can use the fact that cat of x to the n is less than or equal to cat of x, cat of x. So we want to use the fact that cat of x cross x is less than or equal to 2 cat. I think this was fine. I think I just got myself confused from what is this is less than cat of x to the 10. This is 2 cat x minus 1. But I then generally look at, so we keep generalizing this, and for the n case, you get that TC n cat is less than or equal to n cat x minus n minus 1. Okay. And just as before, one can get a, one can consider UIs whose product is non-zero and which under delta star. So here now, there is again a diagonal map as before from, so we can do this kind of a thing as before. So here now x goes to the product x comma x comma x. And just as before, we can look at elements in the kernel of this diagonal map and check what is the largest R for which their products are going to be, product is non-zero, and that will give a lower bound on TCN of x. Okay. So as before, this is not a very satisfactory lower bound, or it may not be a sharp bound all the time. So what we want to do is generalize use the idea of weight to compute a lower bound for TCN of Seifert fiber manifolds. So just from knowing the fact that we know that cat is going to be 4 for such manifolds, we can easily compute an upper bound on TCN of m. It's going to be bounded by cat times n minus 1, which is equal to 3n plus 1. So now we want to generalize the ideas that Faber and Grant used in their paper. And we generalize it to the case of x to the n. So given any map, continuous map f from x to the n, it is given as a n tuple. And we show that the genus of f star pi is less than or equal to k if and only if we can find an open cover on which all these maps agree. Okay, any pair of these maps will agree. Okay. And then we also generalize the idea that in this case, if mu is a stable cohomology, this should be operation of degree I, with xs greater than or equal to n, then for any v which is in hm, if we take this element v bar ij, which I just have written out here, then mu applied to this element will always have weight greater than or equal to 2 with respect to this fibration pi prime, right? And what is this Vij? So in this case, it is just projection, the value of P star on when I take it projected down to ith projection and subtracted by jth, where I is not equal to j. So the arguments work very similarly. So I won't repeat these arguments, but I will say how this helps us compute the lower bound for Seifert fiber manifolds. All right. The idea is to be able to find some cohomology class which will have weight bigger than or equal to 2. So we first, so remember there were these degree 1 elements in the cohomology of M. So I'm doing this for the case of MO, and the same sort of idea will work in the case of MN. Since I didn't write down the cohomology, I guess. So we take alpha 2 and alpha 3, and on these with these assumptions, what we are able to say is that if we take xi to be p star ix minus p1 star x, where I is not equal to 1, then this will be a zero divisor in this sense. And one can check that, so it is clear that this should be a zero divisor because the projection is the same onto both these elements. Sorry, I should take bar of this. I'm so sorry. I don't think I wrote this properly. Okay. So when I take the projection here, this basically looks like, I basically mean the element which looks like this tensor, and there is a x in the ith place. And this sort of looks like x tensor. Okay, so these are the elements in the product cohomology class. Okay. So then when I apply delta star to it, then these both go to the same element and you get 0. So it's clear that it's a zero divisor because it will just be product of these elements. So one can verify that when we take these elements and take their product over I going from 2 to n, then this will turn out to be non-zero, right? Under the assumptions that we have made. So similarly, we will choose y to be alpha 3, and now we consider pi star y and minus p1 star y. Okay, so this is again like an element which looks like one tensor, some y in the, this is ith position, minus y tensor 1. And then we want to consider the Bochstein of this element. Okay. So using the generalization that we gave earlier, and the fact that the Bochstein of y is just alpha cubed square, we can verify. So first of all, using this, we can verify that when we take the product of Bochsteins over all these various I, so I meaning this is varying here from 2 to n, this will give me a non-zero element. And the previous statements basically tell me that this element will have weight greater than or equal to 2. So in particular, so this is the largest product that we are able to construct, which is non-zero. And so all these elements have weight 2. These will all be elements of weight 1, and this will be an element of weight 2. So in all, this basically gives us a lower bound, 3n minus 3 plus 2, which is 3n minus 1. So sorry, I think so this is strictly greater than that. So basically what this tells us is that TCN of n lies between 3n plus 1 and 3n. Okay. So I'm actually, sorry, I think I went very fast. I'm sorry about that. The other thing, so these are all the, some of the references that I mentioned. Okay. This is where I'll stop.
All right, everyone, I think we should unmute and give Rekha a hand.
Thank you.
Thank you for a nice talk. Are there any questions? Well, let me mention one thing that Jose Gomez Larrañaga posted in the chat. For closed three manifolds, we know what the category is. If and that's part of his work with Acuna, I think, right? Jose, are you there? And also Rudyak and I did something like that. So we know category, but TC is still a mystery, I think.
Yeah. So so the only reason I mentioned the CAT result is because we want to use it to compute the TC in this case, but not claiming it's new.
And secondly, so I guess in the Bryden-Zvengrowski result that you quote, you really do need exceptional fibers. You can't have, say, a principal bundle, right? Yeah,
I mean, so the A1, B1, yeah. Sort of
yes, we need those. Because, of course, you know, there's this three-dimensional nil manifold that we still don't know the TC of. And Mark Grant proved that TC is less than or equal to 6. So we know that. If we also could use your result, then we would know it was equal to 6, but we can't, evidently, because it's a principal bundle over the torus. So it doesn't have any exceptional fibers.
So in this, like, we assume that in the AI, BI, the AI always has to be non-zero. So
yeah. Okay. Any other questions?
Yeah, I was going to ask, sorry, about the upper bound, because you mentioned that if there was a nice circle action, you might be able to bring it down by 1. So
shameless self-promotion, Mark.
Oh yeah.
this is based on your work.
John just promoted for me, but at the end of that paper, I talk about like group actions and when this can be used to bring TC down. And I think I had an example of like a Briscorn variety, which may or may not be a Seifert fibered thing, where it worked quite well. And I think there's work like understanding this circle when there's a circle action and when it's kind of free or semi-free. I don't know if you've looked into that.
So we actually looked up a lot of references, but we're not able to. So there are a lot of work where they say it is fixed point free, but that's not quite what we want. So but I mean, it is something that we did think about like we did see your paper, and that's why we thought that we could do better, and if we could find a free action. But all the literature that we know of was only talking about a fixed point free action, which is sort of, I don't know if in that case one can say something or not.
Well, you know, for Seifert manifolds, it's a free action except on the exceptional fibers, where that if you look at the solid torus around a circle fiber, then the core actually has isotropy that's, I guess it would be, what did you use? A and B. So it would be the A, I guess. Z mod A. So, so it is a special kind of manifold. Who knows?
But yeah, I mean, I guess whatever is your result, that cannot be used directly, but maybe there is a way to sort of do it for these special cases and say something. But that's something that we are thinking about, but we haven't gotten anywhere yet with it.
I should mention that all the results in my paper are inspired by a paper of O'Preyer and Walsh.
Any other questions?
Yes, I do have a question.
Yes.
Do you have a very nice, thank you very much for the talk. Do you have an example of fiber Seifert manifold for which one of these invariants, say higher TC, is actually described completely?
We haven't tried doing that. It's something that we should.
The question is motivated by the following fact: the two-dimensional analog, but I don't know how much it is analog. But well, Dan and Lucille proved that, say, for instance, a flame bottle TC2 is maximal possible, but you have to work really very hard to prove that. but for higher TC, the proof is very simple. Just again, zero divisors. So I was wondering if something similar to that would hold for some examples that of the manifold that you're considering.
No, it's a good question. Thanks. I think, yeah, we should think about it.
So, can I say something?
Yes.
Yeah, no, I think Navnath.
Yes.
No.
Yeah. So, for example, on lane spaces, we can have free S1 action. And lane spaces can be think of as Seifert fibered manifolds.
And yeah.
That's interesting.
Yeah, for those, I guess we can give.
So in that case, one can get the exact value of TC.
Mm-hmm.
Exactly. This is a recent result of whoever is talking. I think there is a person that have more or less recently computed the TC
Yes. Lane spaces. Yeah.
Yes. So what's the idea again in that case?
So the similar thing. So the lower bound, we can get it using this. I think Professor Mark Gant in his paper computed the TC of lane spaces. For some cases, they computed the exact value, and in that so there they used the upper bound on the total space of TC as the product of the category of. So the lane spaces can be think of it as a total spaces of fiber bundles, and there they use the upper bound on the total space of fiber bundles, which is less than the TC of fiber times cat of base space cross base space. So there they use this upper bound to compute the exact value. So which is same as the 2 times the dimension. Okay. And so in general for higher TC, like one cannot expect that the upper bound on the total space of fiber bundles, which can improve the dimensional, the usual dimensional upper bound. But in case of lane spaces, having group action, it will improve the upper bound. So lane spaces has this free S1 action. And that's why we can, like, we'll be able to improve the usual dimensional upper bound.
So the thing is that in those cases, the answer is smaller than maximal possible?
Yes, it is the one lesser than the maximum. I mean, it is exactly the k times the dimension. I mean, if n times the dimension, if we are talking about n TCN.
Okay, thank you.
Thank you.
All right, I'm going to stop the recording right now, but if anyone has any other questions, you can ask.